Okay, geometry team, and welcome to Unit 5. We are ready to begin our special right triangles. And when we do special right triangles, we're going to be doing a lot of things involving radicals. And no, we're not talking about social radicals that are creating a revolution. We got plenty of that going on in our world right now. We are talking about mathematical radicals. And this is going to be this lovely little check mark sign that you usually see on the front of your van's clothes. Okay? That little symbol there is called a radical. Okay? And that symbol tells us how to find the square root. You may not be able to see the word radical there because of the glare from my board, and I'm really sorry. But that's the word radical, just like you see up here. Okay? And the radical takes the square root of a number. And the number inside is technically called the radicand. You don't need to know that, but I'm filling in the blank because you were curious about what went there. Okay? And so we're going to go through and figure out where we use the radicals. Some of you know, but we're going to do a quick refresher anyway. So to start off with, if you have the number 1 and then you square it, you times it by itself, you get the number 1. You take 2 and you square it, you get 4. And then 3 squared is 9, and then 16 and 25 and 36 and 49. And you should be filling all these numbers in, or if you have the printed one out that is already filled out, it should already be here for you. And make sure I don't screw up. 144, 169, 196, and 144. These are all called perfect squares. And the reason they're called perfect squares is because you get them by squaring whole numbers. Any other number in between all these you get by squaring a decimal, an irrational decimal that goes on forever and is a pain in the neck. And so these ones are nice and perfect because we got them from a starting pretty whole number and squared it to get a pretty whole number. Okay? The radical is going to take a number and go back to its square root. And so if I take 16 and square root it, I'm going to go back to whatever that was originally, which is 4. And in general, anytime I do a square root, so if I had something squared, the opposite of squaring is the square root. So to take the squared off of a number, the square root is the inverse operation. So I'm going to have x squared, the root and the squared cancel each other out, and you end up back with whatever the starting number was for your problem. Okay, so perfect squares, square roots, radicals, we're ready to move on to more complicated things. I know that we do not have my pretty slideshow here because you know what? Sometimes I just don't get around to the slideshows. And we're going to use, this is what the kids in class get to do every time. So, opening this up now, we have some rules for radicals. And the first rule for our radicals is you cannot have any perfect squares except for one underneath the radical. So if you see this, you have not simplified your radical. That's no different than a fraction you haven't simplified. You're not supposed to have this. So if you were to see something that has a perfect square inside it, you simplify it by working out what is the square root of this. It comes out to be 4, and that's what we're looking for. No square roots no perfect squares under that radical. The second rule is that you cannot have fractions inside the radical. So you don't want to have something like this under your radical. That's not acceptable. You can have a radical inside a fraction, just not the other way around. So you can have the square root of 3 over 4, which you can't see because it's perfectly in the glare. Let me move it. The square root of 3 over 4, that's okay. Because here we have a radical embedded inside a fraction, but the whole fraction is not underneath. This is bad. This is good. The last rule is that you can't have radicals in the denominator. So this is okay having the radical on top, but you could not have something that had like, oh, that's not what I wanted. Something like 2 over the square root of 7. That would not be acceptable. And we will be talking in a minute what to do when you see that. But for now, if you see that, hiss, boo, bad, don't do it, we're going to have to fix it. Okay? So those are the start of our rules for our radicals. So, examples of what to do. You look at this first guy, I've got the square root of 12, and you think, oh, that's great, I'm following all my rules. But you would be wrong. That is actually not following all the rules, because there is a hidden perfect square inside here. So this is where you have to memorize or know as well as you can all those perfect squares, because when you look at 12, that's actually, if you break the 12 up, that's actually 4 times 3. And 4 is a perfect square. And so we don't want that 4 underneath the radical. Now, our rules for radicals allow us to split up multiplication under a radical. So the square root of 4 times the square root of 3 is really like the square root of 4 times the square root of 3. And now I can take this perfect square that's in that radical and simplify that portion of it. So the square root of 4 becomes 2, and the square root of 3, well, that's some ugly number, 1.4 something or other, I don't remember. And so you can just leave it as a radical and never have to actually know what the decimal is until you have to get out your calculator and do it. So this would be the simplified radical for the square root of 12. So to simplify the square root of 18, you start thinking, what multiplies to make 18? And are any of those things perfect squares? And so you start running through your perfect squares. 4 doesn't go into 18. 9, my next perfect square, does. And so I'm going to break this up into the square root of 9 times 2. 9 times 2 was 18. And then you go, oh, I can take this perfect square out now by doing the square root of 9 times the square root of 2. And that square root of 9 becomes 3 times the square root of 2. This is simplified, this is not. So one of our rules in math was always simplify your fractions. Well, you also have to simplify your radicals. You look at the square root of 27. You think, what multiplies to make 27? Oh, that's 9 times 3. So this is the square root of 9 times 3. And now I break that up. The square root of 9 times the square root of 3. That one simplifies. The square root of 9 is just 3, and then times the square root of 3 just falls down here. Okay? And there are more examples. The square root of 36, that one's a perfect square already. You already know that the square root of 36 is just 6. Yay, it comes out to be a pretty number with no radicals at all. Then you get to this guy here, the square root of 10. Well, no matter how hard I try, I can never get anything to multiply underneath it that's a perfect square. Well, that's okay. That just means that the square root of 10 does not simplify. There are no perfect squares to pull out, so you can just leave it as the square root of 10. There's no extra work for you left to do. Okay? Erasing so that we can move some stuff up and keep going. So when you come down here, what if you already have a number times by your radical? You keep doing things the same way, you just happen to have an extra number hanging around. So this is 3 times the square root of, and now let's see if we can break up 28 and pull any perfect squares out of there. I think 28, that's 4 times 7. So I've got the square root of 4 times 7 actually hiding out inside that radical. Well, to simplify that, I know that the square root of 4 is a perfect square. And so 3 is still hanging there. I have broken out the square root of 4, and I still have the square root of 7. I can simplify this. So I still have my 3. The square root of 4 is 2, and the square root of 7 doesn't simplify. Now to finish this, let's combine our like terms. I have these two pretty numbers now. I can go ahead and multiply those. 3 times 2 equals 6 times the square root of 7. So 3 times the square root of 28 actually simplifies down to 6 times the square root of 7. Who knew, right? And so you can come over here and any one of these, see if you can simplify them. 2 square root of 200, hopefully it popped right into your head that, oh, 200 is just 2 times 100, and 100 is one of our perfect squares. So you know that 2 times square root of 100 times 2 will be 2 times the square root of 100 times the square root of 2. The square root of 100 is just 10. And in the end, we end up with 20 times the square root of 2. So each time I break up my radical, simplify the parts that simplify, and combine anything that needs to be combined. What happens if you have a negative number? Don't panic. They still multiply. 3 times the square root of 32, or negative 3. Well, that's negative 3 times 32. Now you think, well, that's 4 times 8. And that would work. Okay. But when I break this up, the square root of 4 times the square root of 8, that's negative 3 times 2 times the square root of 8. The square root of 8 still simplifies. It's not the simplest thing. I can still break this down into the square root of 4 times 2. And then keep going from here. So then that would be the square root of 4 times the square root of 2. The square root of 4 simplifies into 2 root 2. And then all these other things that I had already simplified out come down. And so you have to watch out and make sure that your radical at the end doesn't still simplify. And so here, 2 times 2 is 4 times negative 3 is negative 12 root 2. If you want to avoid this thing, back at the beginning when you do this, I'm going to come over to this space, but I'm not going to focus on this problem. I could have taken this and realized that, is there a bigger perfect square that goes into 32? Well, I knew that 4 did. And then you think, okay, does 9 go in? No. What's the next perfect square? 16. 16 goes into 32. 2 times 16 makes 32. So now I could say negative 3 times the square root of 2 times the square root of 16 here. And now I can simplify that square root of 16. So I have negative 3 times the square root of 2 times 4. And then I can go ahead and combine my whole numbers. The negative 3 times the 4 is negative 12. And we put the whole numbers always in front of the radical. And then the radical always goes at the back. So I'll have negative 2 times root 12. So you can call it negative 2 times the square root of 2. Sorry, Mrs. Cerna, negative 12 times the square root of 2. Or you can say negative 12 root 2 if you want to be lazy and make it short. As long as you specify where the square root is, we're good. And you notice you get the same answer either way. Mrs. Cerna, that's a lot of stuff to keep track of. Well, yes, but they're not big. Stay organized and orderly, and however much there is, just keep bringing it down, and it's going to stay organized. So those of you who like to just do stuff in your head, don't do stuff in your head. Pull it down nice and tidy so you don't lose things. I lost my mind years ago, and so I have to be really careful not to lose my math. Okay? Over here, I have the square root of negative 100. And you start thinking, what multiplies to make that? That's going to be the square root of 100 times the square root of negative 1. Oh, okay, square root of 100 is 10 times the square root of negative 1. I don't know what the square root of negative 1 is. Okay, we'll just leave it then. That's totally fine. Leave it there. Incidentally, the square root of negative 1 is considered the imaginary number, because what times itself makes a negative? Not any of the numbers you're used to using. And so for a long time, people thought this was imaginary. It has since been discovered it gets used a lot. You're not going to use it much, so we're just going to leave it here and let it sit and do its thing. Just know, if you get this, don't panic. Just leave it where it is and walk away slowly. Okay? What if you have a fraction? I don't want a fraction in my radical. So you go, okay, you can still break this up. This is the square root of 49 over the square root of 36. And you can then treat these as separate things. The square root of 49 is 7. The square root of 36 is 6. You're done. Walk away. Square root of 5, square root of 81. You can do the same thing. You can put the square root on top and the square root on bottom. You end up with a radical on top, and you end up with a whole number on bottom. This is okay. Our rule said we can't have radicals on the bottom, but it's okay to have radicals on top. So this is okay. You leave it like it is. Our last example here that I'm going to go over with you, I've got the square root of 18 over the square root of 18 25ths. That's going to be the square root of 18 over the square root of 25. Well, the square root of 18 is not simplified. You go, oh dear, that's really the square root of 9 times 2. And on the bottom, well, I already know that that's a perfect square, so I have a 5 on the bottom. Well, I'm going to keep simplifying to go on this, and I go, oh wait, the square root of 9 times 2 is the same as the square root of 9 times the square root of 2. And now I do have that perfect square, and I have 3 square root of 2 over 5. And so just keep breaking things down. Look for those perfect squares that we showed you on the first page as factors, and you're going to be able to be fine and do the stuff. Okay? But I know what you're thinking. You're thinking, Mrs. Sterna, what happens if I do end up with a square root on the bottom? What do I end up doing there? Okay, so I'm going to move this up. We're not going to focus on down here, but I just need a blank space so that we can start talking about those. So what happens if I get the square root of 16 over 50? Well, that's not a simplified fraction anyway, but focus less on that and let's focus on simplifying it. So you think, okay, to simplify this, I have the square root of 16 over the square root of 50. I can always break up a fraction under a radical into the top and bottom, the numerator and denominator. You go, okay, on top here, I know that the square root of 16 is 4. On the bottom here, let's see if we can break up 50. 5 times 10, neither of those is perfect squares. 2 times 25, so I have the square root of 2 times 25 on the bottom here, which I can now simplify out. I have 4 over the square root of 2 and the square root of 25. And that square root of 25 simplifies. So now you have 4 over, and the square root of 25 is 5. I'm going to put that number in front and then leave the radical in back. So now I have 4 over 5 root 2. And you panic. And you go, oh no, Mrs. Sterna, you are breaking one of the rules for radicals. I'm not supposed to have a radical on the bottom. This is where we're going to do something fancy called rationalizing the denominator, which is a big fancy word for let's get that radical out of there. So I'm going to bring him down here and go, okay, I've got 4 over 5 root 2. And anytime you want to change a number so that it looks different but has the same value, we are going to multiply by 1. Because timesing by 1 doesn't change anything. But the way we make it look different is we use the number 1 in disguise. And the way we do that is we do a radical over a radical of the same thing. So I've got this, I'm going to put this on the other side here. So square root over square root. Anything divided by itself equals 1. So if I times this by a radical over a radical, I haven't changed its value. I'm just timesing by 1. Okay, well, the way you decide what to times by is this radical underneath here. If I don't want the square root of 2 here, I'm going to use a magical 1 that has the square root of 2 on top and bottom. Trust me on this. You may not understand why yet, but trust me anyway. We're going to times by this fraction 1 that happens to have the square root of 2 in it. And you go, okay, 4 times the square root of 2 is 4 times the square root of 2. On the bottom here, I have 5 times the square root of 2 and the square root of 2. And now we're going to use a little bit of common sense here. 4 root 2, well look, what is the square root of 2 times the square root of 2? Well, our rules tell us that two things multiplied under the radical, you can just combine them under there. So the square root of 2 times the square root of 2 is really the square root of 4. And this is really the number 5. So I've got 5 over root 4. And you say, Mrs. Cerna, that didn't help. I still have a radical on the bottom of my fraction. But this radical contains a perfect square. And so now I have 4 root 2 over 5 times, and what is the square root of 4? Oh yeah, it's 2. Oh, Mrs. Cerna, this is taking so long. Sometimes things take a long time, but they're not intended to be hard. They're just annoyingly long. And you go, okay, this is equal to 4 root 2 over 10. Oh, the radical is gone. Yay, that's what you wanted. Now, we just have to simplify the whole numbers, because fractions always still get simplified. 4 over 10 simplifies to 2/5, and then that root 2 just hangs off there on the end. Yes, it seems like a long string, but just focus on one little piece at a time, and you're going to be okay. So I'm going to put a new, fresh problem up here and walk you through it so we can see how it's done. So I've got, let's see, the square root of 5/11. Okay, to start out, we're going to break that radical up into the numerator and the denominator. And then we say, I don't want the denominator to have a radical, so I am going to times by 1. Same thing top and bottom. I'm going to use this thing that's on the bottom that I don't want and put it in both places, and that's going to help me get rid of it. And so in the end, I have the square root of, well, 2 radicals multiplied, you just multiply the radicals. So 5 times 11 is 55. And notice there were no perfect squares in there anywhere, so I'm not getting anything that's going to simplify here. And then the square root of 11 times the square root of 11 is the square root of 121, which, hopefully, as you get more comfortable with your perfect squares, you're going to go, ooh, that was 11 times 11. That's a perfect square. And so the square root of 121 is just the number 11. And on top, 55 doesn't have any perfect squares hiding in it, so I'm just going to leave it as whatever the square root of 55 is. It's 7 point something or other that we don't know, and so we leave it like this because this is a lot prettier than a decimal that goes on forever. Okay, so now you have a simplified radical fraction that is ready to go. Why did we bother learning all of this stuff about radicals? Well, we're going to be using it in our unit. But to start off with, we're going to use it with an old friend of ours. And that old friend is the Pythagorean theorem. Okay, there we go. And so our Pythagorean theorem is a good old friend of yours if you know your ABCs. Just do not try and do these things in your head. Please, for the love of all that is mathematics, always show your work. So here, the Pythagorean theorem is used to find the missing side, oh, that didn't show up very well, of a right triangle. So this only works in right triangles. If you can remember that, you're set. You're like, Mrs. Cerna, I may have already learned this before. Good. So A and B are sides that are called legs, and these are the two sides that come off of your right angle. So the legs are the ones that touch the right angle. They're adjacent to that angle. Side C here, the one that's straight across from your right angle, is called the hypotenuse. And the hypotenuse is always going to be the longest side in a right triangle. There it is. And so for any right triangle, our Pythagorean theorem is a squared, one of those sides squared, plus b squared, the other guy squared, will give me c squared. That's the hypotenuse squared. Notice that the hypotenuse here is squared. And so sometimes we're going to have to unsquare it, and that's where those radicals come in. So looking down here, I know it's kind of faint, but I'm going to give you the numbers that you can't see. I have a right triangle here. There is a little mark here in the corner. This side is 7, this side is 9, and this side is x. And I want to find x. So I go, okay, I am going to use my Pythagorean theorem. So one of my sides that comes off the right angle, one of my legs, is x. So it goes in for A. One of my sides is 7. That will go in for B. And then the hypotenuse is always C. Every time, no matter what. So my hypotenuse here, 9, will go in for C. And you start working it. X squared plus 49 equals 81. I have to subtract the 49 from both sides, and I get x squared equals whatever 81 minus 49 is. Let's see what it is. 8, that'll be 7, so 30. So I have x squared equals 32. Putting it up here so you can see it better. Well, I don't want x squared. I just want x. So I think, what is the opposite of squaring so I can get this squared off of here? And that is my square root. And if I square root the left side, I square root the right side. So now I have the square root of x squared. The squared and the radical cancel out, and I'm left with just x. For the square root of 32, I need to simplify this. But we simplified this one before. That's the square root of 16 times 2, which I can then break up and go, oh, the square root of 16 is just 4. So x equals 4 times the square root of 2. This is why we needed to know how to simplify radicals, is because we get these answers that have radicals left in them, and you need to know how to simplify them. And see, you're almost done. Down on this problem, I've got a right triangle, I've got an 8 for a leg, I've got a 13 for a leg, and I don't know the hypotenuse. So remember, the hypotenuse always gets to be the C number. It doesn't matter which one you put in for A and B. So I'm going to go ahead and put 8 squared plus 13 squared equals x squared. Now you helps to know these. 8 squared is 64 plus 169 equals x squared. Let's simplify it out. 64 plus 169, I'm going to have to add this here because I don't know how to do that in my head. 9 and 4 is 13, 6 and 5, 13, so that's 233 equals x squared. Okay, I need to simplify this now. Does 233 have any factors? This is where you break out your calculator. It's not even, so it doesn't divide by anything even. It doesn't divide by 3. It doesn't divide by 5. Does it divide by 7? You get out your calculator and you check. And you check and check and check. And after you have simplified everything, you unsquare the square, you end up with x equals the square root of 233, and that's not going to simplify. The square root of 233 for x doesn't come out to be anything. This does not actually simplify once you run through all the possibilities, and that one gets left just as it is. If it doesn't simplify, even if it's ugly, you leave it like it is. For this last guy now, I'm given that this is 14, that this is a right angle, this is 29, and we want to know x down here. And I've got some other junk in here that's going to try and mess me up, but I don't need to worry about that junk because I just need to focus on this big right triangle. And so these two must be the legs because they're coming off the right angle, and this is my hypotenuse. So 14 squared plus 29 squared will equal x squared. And this is where you would get out your calculator and figure out what is 29 squared. I don't have a calculator in front of me because I was not that well planned. So I'm going to have to do it in my head. 9 times 2 is 18, and 8 is 26. 18 here, 4, 1, 5. So 1, 14. So that's 841. Great big number. Calculators are good. 14 squared is 196. And so I end up with some incredibly large number here, equals x squared, but don't panic. You still just square root to get the squared off of here, and square root to get the squared off of that side, and then you will see if this comes out to be a nice, pretty number that divides. It doesn't divide by an even because it's odd. It doesn't divide by 5 because it doesn't end in a 5. It doesn't divide by 3. If it doesn't simplify, you leave it where it is. If it does simplify, you simplify it down. Okay? So, good luck using your Pythagorean theorem and your rules for radicals. Email me, Zoom me if you have any questions. Have a great day.